Welcome back. It's the second installment of Universal Sister Algebras. Gilles, go ahead. It's all yours.
Okay, so on Monday, I talk about the construction of the three-star algebra over any star ring. Now we're going to focus only on complex numbers, as we want to work with sister algebras. And at the end, I talk a little bit about adding relations to these algebras, to these three objects. So in most, not the most, but in several instances, when you have an algebraic structure that you want to present using generators and relations, you take the free object and then describe a quotient of this free object to satisfy the relation that we want. For sister algebras, this does not work in general because we don't have a free sister algebra. So in order to construct the sister algebra, satisfying the relation that we want, it's going to be together with the generation. It's not going to be a quotient of a free sister algebra because there is no free, but nevertheless, if the relations themselves satisfy certain conditions, we can build an algebra, sister algebra satisfying those relations. So I want to talk a little bit about these relations. Sister algebras. I mentioned on Monday that there is a paper by Gary Loring where he describes these relations in a more categorical way. But I don't think that the relations that he defines covers all the relations I want to work with. I want to explain a little bit more about this later. But the idea is that once some operators on a Hilbert space satisfy certain conditions, and the relations themselves, not necessarily inside the sister algebra, but maybe in a representation of the sister algebra. And so I'm going to talk about two kinds of relations. So first, just to pick some notations. Instead of using X that was using on Monday, I'm going to use G for a set. So this is the set of generators. But I'm going to suppose that's non-empty. And I'm going to write f of g, the free star algebra generated by g, of the free star algebra is the complex numbers generated by this set G. And as I mentioned on Monday, by representation of this algebra, I'm going to think as a star homomorphism in a bounded operator on a Hilbert space. A representation algebra, a Hilbert space. I'm going to think this as a star homomorphism. And because it's the free I'm going to row for this representation. And because it's freely generated by the set G, it's enough just to give the operators for the generators. Not the MNOT operators. And that's that. Not too confused. And the idea is that in a way, we want to this operator to satisfy certain conditions. So I'm gonna talk about two kind of relations. In theory, I guess we can talk about any other kind of relation than what I'm gonna talk about here. With that, I'm gonna focus on these two. So this is the one that was originally in Blackduff's paper, although he didn't call this normal relation, just call a relation. And the idea here is that it's going to be just a pair. Let's call X F, where X is an element of the algebra generated by that. It's a non-negative. So what does this mean? This means that we want that the norm of this element X to be less or equal than this number X. So this is what this pair represents when you want to think about this relation. Usually we are more interested in relations where there's an equality. So for equalities, and use f equals to 0. So, for instance, if you want to say that a certain element is a projection, you just add two relations. You can write this as P once P star 0. So this means that P is self-adjoint. We add P square minus P 0. And this means that the element is an idempotent. So you can always, if you want an equality, which is usually how it's presented, the relations, we can always add the 0. But this is more general than the medium. I'm going to give an example later, which appears in Alma's mini course, which is the continuous functions on the closed disk, where we needed not only a normal element, but we need to bound the norm of this normal element by 1. So this is a relation that we can allow in this setting, because we can just say, using the pair x1, to say that the norm is less or equal than 1. And with this relation, then we can prove that we can find the continuous function on the closed disk as a universal sister algebra.
Sorry, yes. So to say that P minus P star is 0, you are imposing a norm relation.
Yes.
So taking eta equal to 0.
Yes.
Which means that this difference must be 0.
Yes.
Okay.
Yes.
What about nilpotence in the algebra? So they cannot exist. Non-trivial nilpotence cannot exist in a sister algebra. But how can you avoid them? What's the mechanism here?
The problem is
and why you imposing this self-adjointness of P as this norm relation, the P minus P star comma 0. What would be wrong if you write P minus P0 is equal to 0?
That's not wrong. That's still
it's
still a valid relation.
Mm-hmm.
After we construct the sister algebra, what may happen is that the relations kind of forces that element to be 0. So in a sense, the 0 sister algebra satisfies any relation that we want. So it may happen, let's say, if you want to put Yes, so something like p to the n equals 0. Just put an element here, then this is going to force the element to be 0.
Yes, but this approach using norms is more general.
More general.
It's more general.
So if I take a generator, let's say Q, and I have the norm relation Q to the power n or Q squared,
Yes.
comma 0, it would mean that that
Q is 0.
that Q is 0.
Yes.
No.
Why? I don't understand.
No, you can have some. I think that the problem with nilpotent element is that in this definition is
Joint.
for self-adjoint is equivalent, but for general.
But I like to understand.
No, but the problem is the
Depending on this universal
Tomasz, in
level.
the definition of nilpotent element is a potential quantifier. So I think that there is a problem there. How to express that there is some n. If you consider that algebra generated by relation, you impose all of these relations.
Yes, that's true.
You cannot impose all possible relations. Somehow have saying that the element is a nilpotent, you have to specify with which n it is nilpotent.
And
Only this is
this kind of relations, saying that an element is nilpotent, we can translate this. It's not possible to translate in this setting.
Okay.
Or what thing is this?
This is somehow similar like in model theory. Basics, set theory and then model theory. There is a problem to express this notion of the torsion group in the first language level.
Okay.
So I think that the situation here is similar.
So far, it's just nothing new, but we have to wait to see why we want to introduce this, right?
Yes.
I wonder how you can avoid this self-adjoint nilpotence here, because there is no any assumption about the relation between this norm and multiplication here. And how do you know that your norm relations in representations would give something consistent with the conditions for the norm in the sister algebra, for instance? You are not imposing this sister algebra relation between.
The thing is, once you put 0 here, let's say the 0 element satisfies this relation. So if 0 minus 0 star is 0.
Yes.
Here the same thing. So when you have these relations being equal zeros, there's nothing, unless we know the end result, there's nothing guaranteeing that the element would find 0 is not different from 0. So if you just impose this relation, a priori, we don't know if P is 0 or not. So we need to find a complete representation to show that certain element is not 0.
But at the end of the day, you want to construct this universal object,
Yes.
which is an honest sister algebra.
Yes.
So in which self-adjoint nilpotents do not exist.
The problem is that do not exist.
Non-trivial. They do not exist.
The problem is that these do not exist. I'm not sure if you can translate this as a relation.
Also, maybe the problem is that here this relation does not mean that P is nilpotent. It means that P is idempotent.
Yeah.
No. I'm asking in general.
In a sister algebra, there are no self-adjoint items.
Yes.
So when you take any representation.
Yes, but I'm not talking about representation. I'm asking about the universal object.
But what but the universal object will be constructed from representation.
Yes.
So this is.
So for now, it just
Okay.
So for now, it's just what you want to kind of impose for this element. And as I said, what can happen is that all elements are 0 and the algebra is 0. I say you want to impose that x squared is 1, then x squared is minus 1. Then the only representation that's going to satisfy this one being the identity is the 0 representation, so the algebra itself
Okay, so the universal object will not be given in terms of generators and relations, even if you think about norm relations.
No, it will be given by that.
You must add something to this to kill these things which couldn't
It's gonna happen naturally. It's gonna happen naturally when you take, because what we're gonna do is we have the three-star algebra, and we're gonna construct a C-star semi-norm on this algebra, and then we're gonna take the quotient by the elements where the C-star semi-norm is 0. And when you take this quotient, all thing that goes wrong is gonna be modeled out in the three-star algebra.
Maybe the good thing is, instructive example is to imagine what happens if you consider, for example, this canonical commutation relation. You can write it down, xy minus yx minus 1.
Yeah.
So what does it mean? If this relation cannot be represented on a C-star algebra level, this means that, okay, you can take a universal object in the realm of star algebras, or maybe algebras in general, and then you can consider this ideal, but afterwards you would like to go to the C-star algebraic level. So you need to take a closure of this ideal.
Yes.
So the non-existence of this representation means that if you take this ideal and take a closure, you get something which is the whole space. So this ideal would be necessarily dense. Okay. After writing,
So the universal object would be zero algebra.
yeah, it is not clear whether these relations are such that it would they would admit from non-trivial representation. It is not clear from the beginning. So it could be somehow.
I'm not asking about non-triviality. I would be happy even if at the end of the day, this universal object would be zero algebra.
Yeah.
I'm asking only about the existence.
Yeah, it's always
And how this universal object is presented.
it will. The trick is that there will be always a universal object.
Yeah.
Might be zero.
Yes.
Yeah. That will happen. So my question is, how far we are from the final definition?
Until you see, there's still a bit need. The thing is, there's not all relations are going to be by universality. Okay. We need some condition on the relation. For instance, we have no relations.
Okay.
We know that there's no universality, no relations. And the same thing, if you want to just add being self-adjoint, there's no universal algebra of self-adjoint element.
So sorry. So maybe it would be helpful to us to see first the roadmap. Okay.
Okay.
To see how many steps
Okay.
you have to.
No, let's just write here the other kind of relation, then I'll give the roadmap.
Semi-norm would be a crucial.
So the next step,
Semi-norm and then taking completion, separation completion.
Okay.
What is
Because you are talking about representation, but the meaning of strong operator topology, yes, from step to step. Think patience. Okay.
Yeah,
Sorry.
we just gave two definitions.
Okay. Sorry.
So this is the kind of relation that I've done in a paper for Juliano Boava that, I don't know, it doesn't appear in the literature, and most people avoid using infinite sums. So this is something that it's quite new and it's not really much explored. And I think we can add, I'm not sure what's the name again, that you asked last time about all the kind of topologies. In theory, we can add here all the kind of all the relations as well. So here, I'm gonna just write this SOT relation just as being it's a net. Here is a pair.
I would say that if you are, after all, you would be focusing on projections, then the strong operator topology is a very natural choice.
Yes, it's
Strong operator topology.
Yeah, but put the star to make the star continuous.
No, this S stands for strong.
Yeah, then
yes.
strong star. You can put the star inside.
But this is a different topology.
Yeah,
The star operation is not continuous with respect to strong operator.
you can force it.
So here, I'm doing just write this in a net. of elements in the pre-algebra. And what I want this to mean, I want this to mean that xi converges to 0, but this is with respect to the strong operator topology. Of course, once we represent this in a Hilbert space, I want these elements, when represented in a Hilbert space that converge to 0, that's what's going to be this kind of relation. So this is the kind of thing that I want to impose. So for instance, if you want to write down something like the similar projection, I'm going to use it as an example later, but I say want to give some, for instance, in the graph system algebra, you have something like this. So I have a sum here. I just want, let's see, write this as a limit of finite sums and put it the other way around, and then want this to be 0. So I mean, think this as an even an equality. I want this to be converted to 0 in the strong operator where it has some finite sums.
Okay, so SOT means that we find a representation and then take the operator norm.
Yes, no, not the norm. The strong operator topology.
But any representation.
Not necessarily.
So you fix a vector in a Hilbert space and then you have convergence in the norm, but norm in the Hilbert space, not vector norm.
But it's not for every representation. It's for some representation.
Some.
Yes.
So find one is enough.
Yes. You may pay for representation of the algebra, it's going to be enough.
One is enough.
Yes.
Oh,
You make it
So
precise.
for instance, let's consider the Gonçalves algebra. I think
Even if the representation is not faithful,
Sorry?
even you said that it is enough, even if the representation is not faithful.
no, it's enough to find one representation, one faithful representation of the algebra. Then it doesn't need to satisfy for all representations.
Yes, could you like make it precise? What's the SOT like? You start with some
This is
algebra.
abstractly, it's just a net. A net of
I know.
No, so you are asking how this topology is defined.
Yeah.
So the net converges even only if net, we call it xi, for example, it is already represented in a Hilbert space. So you fix a vector, say xi, and then the net of vectors in Hilbert space as xi on psi tends to 0.
For every fix, that's the
Yes, first, yeah.
that's the strong operator topology.
Yeah.
SOT is, stands for a strong topology.
Convergence in the normal.
Pointwise convergence.
Yeah, convergent. So yes, I think it's better to record that it's a.
No, but it's
So-
important to stress it is out.
Yes, it's a pointwise.
Not pointwise.
Non-pointwise, but yes.
Pointwise, which is weak operator.
Yes, but yes, it's better to.
So let me write this down here. So let's say a representation. Of the pre-star algebra.
So the last line on the previous slide was about this SOT interpretation to be in representations.
Yes.
Okay?
Yes.
It should be in quotation marks because
Yes.
so we have everything is abstract here
Yes.
before representation.
Yes, you only consider those representations.
Here as well.
Yes, I'm happy. Yes.
So more precisely, what we can say is that this representation satisfies.
So even before you represent your object, you are deciding what would be killed in every representation.
Yes, in a sense, yes. Yeah. Let's say it's a satisfied the norm relation.
So it means like this SOT with respect to rho. That's
Yes. But the thing is that it's enough to find just one representation where it's satisfied to build a universal object satisfying the relation. So say it satisfies a norm relation. Except if the norm was
Oh, the first one, we need a representation. I see.
It satisfies. Yes, the relation. That. If I guess can say for all elements in the Hilbert space, can put in normal. Guess it doesn't matter. It's converted to zero. This converted with the converted in the Hilbert space. Okay, so we want to build the sister algebra given a set G, certain normal relations and certain SOT relations. So let me call just to put everything together. There's a definition here. Of this generating triple. Of the triple. Where G is a set. And there's also set of normal relations. And RS the sets from operator topology relations.
Or maybe a stupid question, since you divided those possible kinds of relations into norm and SOT, is it somehow possible to change those sets of relations in such a way that, in fact, it would suffice only to consider SOT relations? Something, I don't know, I'm thinking like,
And the thing is,
repeating many times the same set, and then it would somehow maybe force relation to be satisfied in the norm.
yeah, I'm not sure if
I know that this is not an important question, but
yeah.
being pedantic, yes.
Yeah, I don't know, because one is really converting to zero, the other is bound on the norm. I'm not sure how.
Okay, so
Trick is-
it's also converging, it is always converging to.
Yeah, it's-
Yeah.
The conversion is the bounding.
I think the trick is to introduce inequalities in the norm.
Yeah.
That's fine, but that your norm relation introduces inequalities. So you can have your operators, as you say, bounded on a disk. Otherwise, you prevent unbounded, but you include a lot of representations which have lower norm. That's norm relation is an inequality.
Yeah.
The other one is an equality. The other one is an inequality, and the SOT relation is an equality.
Yes.
Yeah.
Voronovich introduced a very similar notion of a bounded domain.
Yeah.
Non-commutative bounded domain. Yeah. But there was no this SOT condition.
Yeah.
So they are independent. You need both.
Could you say something more about this?
There's a paper of Voronovich about this bounded, non-commutative bounded domains.
Commutative
So,
domain.
But he was constructing this universal sister algebra for the set of algebraic relations and these inequalities.
Yeah.
But without this SOT condition.
You put spectral conditions.
Yeah, spectral conditions instead of this SOT.
Okay, thank you.
So they're independent. You're right.
So I guess now it's the point that we want to build a sister algebra out of this triple. And as you know, not all triples are going to be able to do that. And then there's this definition that is in Blackdar's paper that we just adapted for these more general relations. Is that the triple that would be admissible if every family of representations of for every family of representations satisfying the relation.
So this Rn and Rs, they are finite collection of the relations, or like it could be infinite.
It can be infinite, not necessarily finite. In general, they're going to be infinite.
So in fact, if you allow infinite set of relations, you can restrict yourself to strictly positive numbers in this case of the norm relations. You can impose all
Yes.
norm less than 1/n.
Yes.
Same as imposing by zero.
So we don't have algebraic relations here. All algebraic are inside these Rn.
Yes.
Okay, with eta equal to 0.
Yes.
Okay.
Or maybe infinitely many with eta equal to 1/n.
Yeah. Can also
Very good.
take this as
That's
so it's a very family of representations.
So don't assume that Rn and Rs are small in a sense.
No,
They are arbitrary.
there is no restriction on the cardinality of the sets.
There is maybe with respect to cardinality of G, yes.
Yes, these two are going to be bounded, but it's going to
Yeah, that's really.
although here not
Actually, because more relations than cardinality of the generator.
yeah, you could have because set I of index in the net can be arbitrary.
Dimensionalized. These are worth.
Okay. For RS, yes.
Yeah, so
Yes, so for in fact, this wouldn't be a set anymore if G. Yeah,
Probably it will be a set.
you can always restrict to a set, but it does not follow from this construction.
So do you allow G to be countable, infinite?
yes.
No, but I mean.
So Rn could be like.
Yeah, but in RS, Thomas, in S, consider possible nest.
Yes. RS there's no bounds for the cardinality.
Yeah,
Rn there's a bound because it's a subset of the pairs.
so in other words, in the definition of a net, you have a mapping from some directed sets.
Yes.
You can formally consider something which looks the same, but formally is different.
Yes.
So.
So it's very famous legislations.
It's a tissue context of the set of words.
So you can consider some net x1, x2, x3, and so on. Okay, this is one net. And then you can consider something which looks similar, but your indexing set would be formally different. You consider some ordinal number cross with the set of natural numbers. So formally you have different net. If you,
Yeah, so how they could be similar if indexing sets are different?
So indexing set is you take the free algebra, all words, as you say. You take the Cartesian product, and a subset is a set of relations. You have all the
Yeah,
sets.
yeah.
Yeah, that's like, yeah.
That whether the direct sum.
And you don't assume anything about these Hilbert spaces.
No,
Okay, fine.
It's fine.
Full generality. Don't separate. Okay. Mhm.
but the idea is that be admissible, we want that whenever we have family of representations of these algebras satisfying the relations, when the direct sum is a well-defined representation, also satisfying the relations. So there are a lot of things that you can go wrong here. So first, this formal element here may not be an element in the direct sum of the Hilbert spaces. Even if it is, this map may not be bounded. And if it is bounded, it may not satisfy the relation. So that these three things that we need to satisfy in order to have this well-defined representation satisfying the relations. And this is whenever I have this triple to be admissible.
so once again, the problem, there could be a problem with this, this supremum of this family would be infinite, okay? For this I agree, but how is it possible that this direct sum may not satisfy those relations?
SOT relation.
Since this.
That's what,
Right.
the normal relations, yes, that's fine, but there's also SOT relation because it's limit in the when this alpha being infinite could have different speeds for the convergence of limit.
Okay, so
Yeah.
problem is with this sort of representation.
Yes.
So in other words, if you would from the start restrict only to algebraic relation, there won't be a problem.
Yeah, there wouldn't be a problem. Yes.
Direct sum of representation is always a representation. Okay, but this could.
As long as it's well defined.
Yes. As long as it's well defined.
If you take the same representation infinite times.
No, that's not a problem. If the same representation times.
When you have the same vector infinite times, and that is non-infinite. No.
But then here is going to be an element of the direct sum of the Hilbert space. The same element, because here it's something that the sum of the normal squares should be convergent. So you can't repeat the same.
So, okay, so could you explain what's the meaning of this requirement? I mean, just. What's the intuition behind these requirements?
This is the idea that we want to build a same norm using our representations possible for this algebra. And this admissibility condition is the one that allows us to give a bound in the same norm of the elements of the pre-algebra. So if it's admissible, every element in the algebra is gonna be bounded for our representation at the same time by a certain constant.
Sorry, and me, I hope I'm not anticipating too much, but just as an example to check that I'm understanding, suppose you have an increasing sequence of projections, which is a sequence of algebraic norm relations. And then you want the strong operator limit to equal the identity.
Yes.
So if you take representations of that, which as was suggested, the slow use of the strong convergence is more and more slowly, might it not happen that the direct sum will no longer be strong operator conversion? Always.
If it's the sum of orthogonal projections.
No, so increasing project, well, it's the same.
Yes,
thing.
yes. No, we prove that it's gonna always give.
In this case, it does work.
Yes.
So I think if the relation of this SOT consists of bounded operators, then there will not be problem. Like if all the next exercise are bounded answers, like say bounded in the unit ball or something, then probably it should be.
If all the generators are in a fixed.
Yes.
Yes, probably. Can you? Do we have some simple example which is not admissible? I want to understand this relation.
Let's give an example of something that's not admissible. So let's say you have G just one element, and then you have Rn to be just S minus I star 0. Then you have RS to be empty. So this tuple is not admissible.
You have your norm condition.
Yeah, included the normal condition
No, only one.
without SOT condition.
Why it's not admissible? Because we can consider representations the complex numbers. So we have the free algebra generated by the sets. Let's see, we put this in C. And we'll just take an element S and send this to N. And so when you take the direct sum of N of S, this is not bounded. The norm of the sum should be the supreme of the norms of each of these row N, but because the N go to infinity, here is N is a natural number.
So this is like a non-existence of a free
Yes,
universal sister algebra generated by one set of channels.
yes,
It's not bounded.
yes, because the norm of row N, the supremum of the, I guess, S should be the supreme. It's going to be bounded. I guess it's not an equality.
Okay, so how does it contradict to the definition? Yes,
This is the case. So the definition is that we want this representation to be a bounded operator. So we never have a family of representations. We want the direct sum to be a representation on bounded operator.
Okay, the thing is bounded, okay.
Yes. And when you go here, you have something that's not bounded. That's not admissible.
Okay, this thing is, okay.
I have a question.
Yes.
What will happen if you replace your given representation by a representation when some summons are repeated infinitely many times. Then it would lead to some representation not satisfying.
I asked already this question, that will be fine.
It will be fine.
Yeah.
It will be fine.
You can reveal it. I asked the same question.
It was.
If that's invisible, that's fine. Because if you repeat, they have all the same norm and it doesn't matter.
So what kind of relations it will spoil? This norm or both?
But
Both.
Yeah.
Both. Okay.
The thing is that this definition is good for building a system algebra, but it's not good to actually prove that it's actually admissible.
yeah,
So
Once again, repeating infinitely many times the same representation does always yield something which is admissible.
yeah.
no, because admissibility is in general for all representations. So if it's admissible and take the same representation, that should work fine as well.
Yeah.
If it's admissible.
If it is admissible, okay, so I'm thinking about the following example, that you take your Hilbert spaces to be finite dimensional, and then somehow I suspect that maybe if you impose some relation on finite dimensions, in finite dimensions, it doesn't matter whether it is solved or, but still, okay, there is this problem that for solved you would like your relations to be of the sort that something tends to zero, and here you have inequalities. Okay, I'm not so sure.
Okay, so as I said, the definition itself, it's good to build a system out, but it's not really good to prove that something is admissible. So I'm gonna give a sufficient condition for this triple being admissible. And in case of if you only have normal relations, actually it's sufficient necessary condition. Have these great people. Suppose that so for every generator, yeah, exists a constant. Going to be a non-negative real number, and for every SOT relations, for this why. In the PDF, I just with the bold, but here is a little bit more concrete with bold. So for every there exists and X that for every representation satisfying the relations. We have there's a bound in the norms of the generators. And there's a bound for every element in the net. The same bound, so if the net is uniformly bounded when represented. This is for our I. Then the represents.
We prove it was a free algebra, there's no relations.
If there's no relation, there is no bound in the for the generators.
Ah,
So the idea, just before proving the theorem, just giving an example. So suppose I have one relation which is like the norm is less or equal than 1. Then, well, for this only generator, this is going to be less or equal than 1, so it's going to be admissible. Or more interestingly, let's say you have this two relation that says that an element is a projection. So we know that every projection on a Hilbert space has a norm bounded by 1. So we have this generator being bounded by 1. And so there is a sister algebra generated by one projection.
but how do you pass the words to products of operators that they don't agree, they increase more?
Sorry?
How do you know it for generators? How do you prove it then for words? If you have a
Yes. So
sum of words,
yes.
linear combination, how do you prove it? Because you have inequalities that can grow and then finally it can go to infinity.
Yeah. So the thing is that let's do this even idea.
Every time by the triangular inequality, you have a bound depending on the word.
But
So
Yes.
if you wrong-
your triangle equality it can increase. You want to show that it's not you don't find elements.
but your bound depends locally on the word.
Yes.
Yes, for each
That's
word.
the problem.
Understand.
The condition was local with respect to the generator, and
Yeah, okay, yeah.
So
the
that's
same about the words.
yeah.
Right.
So you could or not? Could you replace this condition for generators by a similar condition for words?
Yes.
The product.
In one direction, it's obvious.
But for all words, then the generator containing the
Yeah.
for all words.
There's, yeah, just about generators.
Yeah.
Does not concern words.
Don't have closure in everything. I was thinking,
Yeah.
I think
I was thinking in the closure already. But
it's something like if you have some word, some polynomial in three non-commutative variables, so you would get the bound of the form, the same polynomial, we've inserted those bounds.
Yes.
Yes, I guess.
Yes.
well, but modulus.
But in other words, what you're saying.
Yeah, no, I was already thinking in the closure.
Yeah, so for every x in the free star algebra generated by G, using these properties of the norm, find a lambda x and again it's a negative real number, so that for every representation again, satisfying the relations. Have that these bounds of the representation is going to be less really for this conflict. Okay. Exactly, because we have a polynomial, we just use all the properties of normal, triangular inequality, and everything, and then have this. And once you have this, then the for everything representation. As you had before, for alpha. This direct sum is going to be a presentation bounded by, I guess, this is going to be well defined.
Can you say what could not be well defined? What's the issue with well defined in this?
Sorry?
So one of the conditions was that it should be well defined.
Yes.
What could go wrong? I mean,
Boundedness.
the boundedness, yes, but what do you mean by well defined in the sense that an element of P of H? Is that
Yes,
yeah.
yes.
Okay, okay.
So things that can go wrong is that if you just take an element here, this could be something that does not have the sum of the squares bounded.
Yeah.
The unbounded. And if it's bounded, then the bound of the operator itself can be unbounded. This is the two things that can go wrong.
Okay.
And then again, mathematical predictions. So this is bounded, and then as we were talking before, it's kind of easy to show that this direct sum going to satisfy the norm relations. That's fine to. Then the thing is to prove that it all satisfies that for SOT relations, and for that, that's why it's important that we have a bound that is uniform in the for all elements in the net, because otherwise you wouldn't be able to prove this. So here's this exercise in getting in analysis. Let's try to here so to prove. So for every SOT relation in every element in the direct sum. We have that the direct sum of alpha xi applied to x alpha equals to and the thing is that all elements in this Hilbert space can be approximated by an element with finite support. And then in a finite support, we can take the maximum. Let's say you have an index where this index
By the way, so if you take a direct sum, we allow like only finity is many.
What is this?
Zero, this is.
Sum of Hilbert spaces,
Okay.
it's the all element sum.
Yeah, oh, sorry. Yeah.
It's completed.
Okay, sorry. Yeah.
So this family could be arbitrarily large, but nevertheless only at most countably many coefficients are non-zero.
Non-zero, yes.
So you have to prove it for the two.
It's an unconditional convergence. So
This is not direct integral. It's just this, if alpha is like more than countable.
Sorry? Oh,
It's
integral. It's direct sum.
okay.
Discrete measure.
Hilbert space tracks.
Mhm.
yes, a direct sum of Hilbert space. So one way of constructing this is using this. So we take all families where we have this convergence. Another way of constructing is taking the all finite, all sequence of finite support, and you have an inner product, and then you complete with respect to this inner product.
So maybe you should put some bar above this direct sum if it's completed. I don't know.
No, because that's the definition of a direct sum of Hilbert spaces.
Yeah, an Hilbert space.
It's
But it's not a direct sum.
No.
Is this a sum?
Direct sum in the category of Hilbert
Yes.
spaces.
Is the sum in the category of Hilbert spaces?
Yes, I think so.
You think so?
gonna be the co-product of Hilbert spaces. Yeah, so the idea is that this X alpha is approximated by an element with finite support. So for the coordinates where this is 0, use this constant lambda x to control norm. And for the others, we can find elements at I0 such that for all I0, this row alpha xi of these coordinates. I guess I should put this there as an alpha here. And here is just the coordinate in the form. Just an idea for the find out in details, but this is the main idea. So So that's why it's sufficient to consider this. And these two conditions are more easily to prove that satisfies than prove that for all direct sums you have that the it still get a well-defined representation.
Can you describe order relations with this formalism?
Sorry?
Can you use order relations like a positive?
In theory, yes, I think. The thing is that I'm not sure. As I said, if you just want to say admissible in the sense of this direct sum, you can use you can use order relations as well. But I'm not sure if this characterization here would be enough to prove that it's admissible.
Okay, but I guess my question is, so if you wanted to also allow for order relations, you would have to add something extra to your setup.
Yeah, for the sufficient conditions, yes. Because here's the thing, here we just have some sufficient conditions. So if you want to add order relations, I'm not sure exactly how we could change the hypothesis here, get that the relations are admissible.
But sorry, you are asking about this particular theorem?
Not
asking
just
about whether
even earlier than the term, just
whether is it possible to encode order relation in this formalism of Rn?
Yes, that's my question.
Anything that you can write in terms of operates in a Hilbert space, in theory you can use as a relation, and you just need to ask these whenever you have a representation satisfying the relations, the way that direct sums also satisfies. So this framework works in general.
Yeah, but the question is how to write a condition for X to be positive in such a way that all these conditions are of the sort as included in Rn. For me, it's not obvious.
Like you can use this fact that say an element is contractive even only if the matrix say 1 on the diagonal and X and X star on the sub-diagonal, this is non-negative. This is a fact. And using this, you can think it as an order relation of non-negative. Norm of X is less or equal to 1 X star 1. This matrix is positive matrix.
How to define positive here?
That's to show that X is a contraction.
Yes.
How about to show that X is more negative?
What do you need?
No, so it's not in terms of
but
X, but it's in terms of the like on the like matrix M2 by M2.
But if that matrix positive means X is a contraction. But what matrix of contraction would show that X is positive?
No, X need not be positive.
But
The question is, how do you describe, say, C of 0, 1?
No, so like I was saying this in terms of like we think the order relation we are thinking in the C star level, right? Given a representation, we are saying we want that like when a row of X is non-negative or something.
No. I think that the question was about what was said before introducing this representation. Am I right? So,
Yeah.
so the question is whether you can include order relation in this formalism of this norm relation.
So order relation is coming from BH only, right?
No, you need to add an extra formalism.
Right.
Yes.
That's I guess what I was asking.
Yes.
How it works?
Yeah, so for instance, let's say you want to say that two positive elements are less or equal than other. You can do this in a Hilbert space. For every representation in a Hilbert space, there's some other elements.
How about imposing relation of the sort element is positive? Is it true that okay, maybe it's not the same, but something like that this is.
Yeah, you can do that. An element is positive for a representation. The operator is positive.
But that means
You can do that.
you have your Rn, then you add another relation, something completely new.
Yes.
Yeah, that can be done.
And it's actually, this is done in Terry Lawrence paper.
Yeah, right. Yes, sure. So, okay, but so with this formalism, you cannot describe continuous functions on 0, 1 as a universal C star with some relations, I guess.
This function 0, 1, I think I can, I think yes.
Compilation in the different operator.
Yeah. This is also
Okay, maybe not, okay, but maybe C, yeah, C, so C0 of open, half open 0, 1, I mean, what I'm thinking of this is the
Yeah, this is a cheat, but C of -1, 1 is star isomorphic.
yeah, okay, fair point.
That feels like cheating.
Yeah, okay, no, all right, okay, yeah.
yeah, some of these algebras, it's already in Baghdad's paper, he writes only using normal relations. But yeah, sometimes all the kind of relations are not in this formalism, but you could add, and the thing just asked me that this direct sum of representation is still a representation, and this is going to work in general.
But could be there a problem with complete probability? Also, you're only summing up representations.
Yeah.
You cannot twist this by some other Hilbert space. You are not tensoring Hilbert spaces here.
Here, no, yeah. But I think in the
Everything which depends on this tensoring with Hilbert spaces cannot be phrased in this construct.
okay, so just to give some examples,
There are much more operations on Hilbert spaces than taking orthogonal sum. You can take for instance, the Fock space, okay?
Yeah.
Whatever, and all these constructions are lost from this point of view. You cannot create universal things satisfying some conditions with respect to such constructions.
yeah, I guess.
No, we don't need that. I think that's the point.
But we don't need.
We don't need to consider all this. We want some representation. That's right. So that's the direct sum is not like a.
No. If we have, so the point is that if we have some representations, some family of representations, we can take the sum, orthogonal sum of these representations.
Yeah.
Yeah.
No, here, what's our goal here? Our goal here is I give you a bunch of, say, a sequence, a net of xi. Okay. Okay. So can you construct a C star algebra like a, in some sense universal, right? Satisfy this this xi, this satisfy this relation, right? It's not about representation. It's like finding one representation. It suffices to sort of to construct the C star algebra we want.
Yeah, but I'm asking what is happening on the universal level, guaranteeing that in some type of representations, different things happen.
Well,
How
then we go back to the definition of this universality.
So this point of view is only about taking the direct sum of representations. Okay.
If you have tensor product representation, it's one part of it.
But maybe it would be easier to digest if these conditions would be replaced by sister algebras instead of Hilbert spaces.
No, that doesn't.
No, it does work.
No, it does not work in general because for this strong operator topology relations, this depends on the representation. So it's not only a condition of sister algebras. That's the difference between what I've done for Julian Bob and what Terry Loring described in his paper using just sister algebras. So in his framework, it's very general. He described a category of functions from a certain X to a sister algebra and take a supercategory satisfying certain conditions. And if that have some kind of universality. But there's a condition that he asks is that whenever you have kind of a representation of a sister algebra and you take a star homomorphism, this is again a representation of the relations. But if we want this to be done not in the sister algebras, but in a Hilbert space,
it's not clear how it completed the diagram here. So we have the relations, let's say it factors through to a Hilbert space. Let's say you have a paper representation, so that the image of this representation is inside the image of A. So in theory, we can just define a star homomorphism directly in A. But if you compose with a star homomorphism, how do you complete the diagram? That's the problem.
So the problem with this phraseology, because maybe this name, universal sister algebra, is a misnomer here, because it's not about sister algebras.
It is.
What is SOT?
I still have to define the universal property.
Okay, I think
I think let's.
the definition,
Algebra equipped with an additional structure coming from SOT.
In a sense, yes.
So you cannot reduce these questions to
okay, so I think the
ordinary sister algebra.
the terminology he gave at the beginning is a little bit misleading. It's because we start with some algebra, okay? So this free is some algebraic construction, right? So you have a generate set G.
Yeah.
F is algebraic, and then SOT is not just algebraic conditions. It's like you cannot just say something satisfies a representation satisfied. That's the terminology he used. The representation satisfied as
We agree. Everybody understands this.
Yeah.
The point is that it is not about sister algebras. The story is about sister algebras with an additional structure by SOT. So this construction is not internal into the category of sister algebra.
No, that's it. So, yes.
So maybe it would be more honest to
SOT universal.
yes. To add something, not to.
yes, but
So this thing that's internal to category sister algebra, I think it's what Terry Lauren has done.
This is very similar to the situation in the context of von Neumann algebra. There is no universal von Neumann algebra generated by relations.
but I guess this.
Yeah, so it's best to.
Yes, and I agree with you.
There is some kind of.
The thing is that if you give it the reducible triple relations, we can build a sister algebra out of that. And this sister algebra is going to satisfy certain universal property.
Yeah, which include this algebraic relations.
Yes. And that's the thing. You build a unique sister algebra out of this data. That's the main goal that you're going to do that.
But maybe this could be axiomatized, this situation. And after introducing some appropriate category of algebras with this kind of SOT.
Yeah, the thing is that the category that I think it's
And that you are constructing the universal object in this category.
yes.
Yes, it would be nicer.
By universal object, you mean an initial object or
Yes, initial object for.
yes. Yes, that's what happens. Yes. I'm gonna try to explain maybe not further.
Decorated sister algebra.
I think we are still in the category sister algebra. The meaning is that what do we mean by relations, right? So algebraically we know what is.
No.
We have still not seen.
It's about sister algebra with an additional.
Yes. But yes, category using this. So I can just describe it in this way. Let's say you have this free star algebra, and then you can build a category where your objects are kind of pairs like that, where you have a paper representation here. And then a morphism between these two objects. You just ignore the paper representation. Ignore the relation between these two things, and then you can define a category here. So it's going to be a category such that this position satisfies, it's a representation of the relations. So the morphism is just a morphism between the sister algebras. And then the object that we're going to construct is a sister algebra here with a paper representation that is an initial object in this category. Okay.
So what would be the notion of isomorphism? it would be spatial isomorphism implemented by unitary or not
No,
necessarily?
no, just a star isomorphism between the C-star algebras.
So
Because as I said, as far as the morphism goes, we ignore the representation in C-star algebra in the Hilbert space.
yes, but I would say that for something which is already represented in a Hilbert space, maybe the more natural notion of isomorphism would be spatial isomorphism implemented by unitary.
Yeah, but that's the thing, because since it is a paper representation, it could have a different representation of the same algebra and not being user equivalent. So the algebra itself may not be, because this is not uniquely defined, this paper representation.
So it's a little bit tricky.
Yeah, and that's the point that why that we try to put in the framework of Loring, how we could complete here. So you can complete this diagram using some kind of relation between these two representations. Then maybe we can use the same framework. But I mean, for me, it's not really clear why. How can you do that?
But what is the relation between SOT and morphisms in this category? Because you are considering some morphisms from this universal construction to some collection of B of H's.
Yes.
Okay? And you have this condition of SOT.
Yes.
But if you have two different A and B, okay,
Yes.
what are you demanding for this map?
This map is what is via star homomorphism.
Star homomorphism.
Yes.
So this
And
somehow does not take account.
Yes. Yes.
Forget about
So
Yeah.
it is tricky. It is.
Yeah. It's kind of maybe
That's
it's
not very
very technical. So for the objects, the SOT relations appear, but for the morphisms, the objects it doesn't. Because the SOT relations are not really seen in the C-star algebra level, it's just only seen at the representation level.
Yeah, so
It's weird, but not sure if you can do this in a more natural way as it's
so then it's hard to understand what's the meaning of this universal property.
Yes, we have not yet reached that.
We have not even defined it yet.
Yeah, so,
So you haven't defined it.
I haven't defined it.
Okay.
yeah,
But as
Sorry. So
but as I was putting that diagram here, so it's going to be an initial object in that category. So we have representations. So we have star homomorphisms between the three-star algebra and the C-star algebra, together with a fifth representation of the C-star algebra, such as the composition satisfy the relations. These are the objects. The homomorphism is just star homomorphism between the C-star algebras, and it's going to be an initial object that's this category. So I'm going to explain that on Friday.
let's see some challenging examples, probably that we will see why we want these constructions.
Yes. Yeah. So examples. As I was saying, if you just want to add a projection, let's say you have a set G, you just have one element, and then you have just normal relations. So now that we have this theorem, this is admissible.
RS empty.
Sorry?
RS empty.
RS empty.
SM, yes. Because we know that for every representation. Well, I guess we can lambda p be equals to 1. As you know that every representation of a projection has no necessarily equal to 1. So using this lambda p, because this element when represented is going to be a projection, we can use this as being 1.
And this algebra is what? It's two, yes?
Sorry?
Two-dimensional, yes?
Yeah.
Am I right?
Yes. Two-dimensional or one-dimensional?
Two dimensions.
0 and 1.
Generated by projection.
Yes.
So it's C cross C, two copies of C.
Yes. Spectrum.
Yeah, it's commutative. Anyway.
Yeah, this is admissible. And another example, a little bit more tricky, I guess. Let's see, I have one union. Multiple many elements SI, and then I'm gonna just describe. I'm not going to give you all the relation, but just saying that use a units. SI are partial isometries. And then for the system operator topology, when is equal to 1. So how exactly do we write this?
Did you want isometries or partial isometries?
Isometries, yes. And as far as the
In this first example, if it's not non-unital, it would be C. Not C cross C.
Yeah,
Non-unital.
yeah.
Right. So
So it,
I forgot what?
sorry, one copy of C?
Yeah, this because there is no the unit.
Yes, but C is unital.
Yes, by accident. Because it's generated by projection.
projection, yeah.
So this projection is a unit. But
Okay.
Yeah.
the composition like P and 1 minus P because there is
You
no.
cannot use one.
Yeah, right, yeah.
So it was P. You were right.
Yeah. So technically our answer just is there's one single relation which is this one. So why is this admissible? Of course, we have to prove everything, but of course, norm of 1 less or equal to 1. Know that the norm for every representation, I guess we're going to put in a different. We have this lambda 1 can just being 1. Use lambda SI also being equal to 1, as you know that every isometry against is bounded. It has a norm bounded by 1. And this is the one that's it's a little bit more tricky, but we can prove that these SI star are projections.
Yeah.
So you have a sum of projections converging some operator topology to the identity. Then we can prove that these projections must be orthogonal. And because these projections are orthogonal, this is going to be a projection. One is again a projection, so we have a linear combination of two projections. Then we can use that for this, let's call this X bar, so elements. Then we can prove that using 2, it's enough. Maybe we can use 1, but I'm not really sure. For certain as well. There are a lot of details to prove here, but can put that this strip is going to be admissible. Okay, so this is as I said, a sufficient condition to prove admissibility, which is much easier than to prove that for every sum of presentations you have a presentation. And for number relations, actually, this is if you don't have this strong operator topology, if it's empty, this is equivalent. So if the triple is admissible, then there are the constants satisfying that that bounds the norm of the generators for every representation. Not very difficult to prove that. And when I learned this theory of universality for the first time, I learned this admissibility condition using this condition on the norms. But when going to the strong operator topology, we weren't able to prove that the converse of this theorem is true. I think it's not, because again, I have this double convergence, because I have a direct sum with convergence. It's not really clear if it's equivalent or not. But if this RS is empty, then it's equivalent.
Sorry, Gilles, could you please explain to me one more time? There's RS equal to the sum to this family labeled by natural numbers of all these 1 minus a finite sum. I'm kind of confused. So you are saying that this relation is satisfied for every natural number?
No, this means that when you take the limit of n going to infinity, this is going to converge to 0 in the strong operator topology.
Okay. Yeah, thank you.
In all
And this does give O infinity.
Sorry?
This gives O infinity.
Yeah, this gives O infinity, yes.
So, but then, not every representation of O infinity is admissible. Because you don't necessarily have this strong operator.
No, but the thing is that not a representation of O infinity is not admissible. It's not also satisfy the relation test.
It's not admissible, has to satisfy relationship.
No, the admissible, I can go back to the definition. If you have a family satisfying the relation, then the direct sum also satisfies the relation. But it's not that all representation satisfies the relation.
So a triple is admissible. Okay, it's the triple that's admissible.
Yeah,
not
it's the triple.
Not a representation itself. And that's the why it is using this SRT relation are not really well behaved, because you can have a paper representation of the universal system algebra not satisfying the relations. I don't know. As far as the finest.
So could you come back a slide? So there is no way to replace this RS written in this form. In the but one line.
This is informal.
If informal, yeah. Is it the only way to formalize this, that this infinite sum is equal to 1?
Yeah.
Why SOT
That's
used here?
I would say that
Right, the same, in the sense of the this tends to 1 in the norm, for instance.
No.
those are projections, so the strong action topology is very much a case of projection.
Okay. Okay. So this is the motivation for SOT.
Yeah.
Yeah.
You have to choose the right topology.
So if you go back to the Krieger paper where they defined the algebra associated with infinite matrix, they just put in a remark that you could use an infinite matrix, and then exactly there's something like this, and then it's to be interpreted as the convergence in the strong operator topology. So let me see if I can explain how do you build the sister algebra out of this data. So I guess next for Friday, then I'll talk about the universal properties of this. And this construction actually can be done more more generally, in my notes, I've written in a more general setting. I'm not sure if the note's gonna be, gonna be available somewhere. So what's the idea here? So the idea here is that you're gonna
read G, Rn, and Rs, yes?
sorry. So the idea here is to consider set of C stars and norms in the tree algebra. This star algebra generated by G. Call this family P. So this is going to be all same norms. Such that there exists a representation that's fine the relations that same norm given by the norm of the representation. By this. So whenever you have a representation of the star algebra, when you consider this norm of the operator when we represent it, this is going to give a C star same norm. In this free star algebra. And the idea is that we want to take the define a C star same norm on this star free algebra by taking the supremum over the set P. So of course we need to show that this is bounded. Yeah, right, this is the position. For every x in the pre-algebra, directed by G, have we take the supremum, these same norms. This is bounded. And this is the reason why the construction works in a more general framework, because really what you want is that this admissibility condition on this direct sum, but suppose not, suppose that the supremum is infinite for some element x. So if the supremum goes to infinity, that means that for any natural number, there exists a representation the algebra of certain Hilbert space that we take and all with respect to this representation, it's going to be greater or equal than n. Because the same norm gives representation, so there is the same norm here, which gives us this being greater or equal than n. So there's this representation like that, and then direct sum is not bounded. When it is not well defined as an element. Right. The on the operator on the direct sum, so the representation is not admissible. Because these representations so I guess that we can do this very generally. So we have a class of representations of this three-star algebra, which is closed under direct sums. Then the supreme is going to be finite, defining some things.
Is it an if and only if? What I mean is, if your relations have this property of this finiteness, then does that imply that it's admissible in the sense of direct sums?
SOT probably will still be a problem.
Don't think so.
Okay.
Because this supreme is taken only in the certain class. So if you don't know if the class is closed under direct sum, so this direct sum might be outside of the class and not give a same norm. So with the proposition, we can define this our same norm. In the free algebra, I'm going to use 3 bars because they're going to quotient out. This is going to be the supreme. For every family or every same norm. So it's bounded by the proposition, and it's easy to prove that it satisfies all the necessary conditions to be a C-star same norm. And I know it's kind of a standard construction once you have a star algebra with a C-star same norm. How we find the C-star algebra out of that? So the first thing is that we take the quotient. So let I be the ideal elements that the same norm is 0. It's easy to prove that it's an ideal because this triple same norm of the product is less or equal than the product of the same norms. It's one of the properties. This is an ideal. More precisely, it's a two-sided ideal. Two-sided self-adjoint star ideals. Then the quotients. The star algebra. And we define a norm of the elements, let's say for X in the algebra. So an element in the quotient in the increment of triple same norms by the U. So since we modeled out everything that goes, the same norm is 0, what happens is it's going to be a C star norm. This is a C star norm. This quotient. And once you have a system norm on a star algebra, we can take the completion. Respect to this norm. The sister algebra. We call modes and nodes. Because we still have to prove the universal property, I'm going to do this on Friday, which I'm going to call this I guess we still have to prove the uniqueness. The universal sitter algebra. Yeah. Let's find the relations. And press. So what we need for this construction to work is admissibility condition on representations. So as I said, if you have any class of representations of the pre-star algebra, which is closed under direct sums, it's well defined, it's still there. We can use the same construction. So in theory, if you want to add more relations other than this SOT relation, let's say you want to add disorder relations, in theory you can do that. The problem is, again, is if you're given a list of relations, proving the admissibility of this list. This, I think, is the most difficult part, which usually is easy for some normal relations. A lot of algebras are defined using partial isometries, projections, things like that, which are bounded by one. So, yes, so in theory, you can do a very general construction. Sure, to have 10 minutes. 10 minutes.
Could you give an example of this norm relation, which is not zero? Like zero is the algebraic relation. Yes.
So I'm not going to prove here, but let me just give some examples. Maybe I try to do this on Friday after the universal property. So as I had before, this sister algebra, let's say, we just need one relation. Yeah, so let's say you have a set G, which has just one relation, one generator. And for the normal relations, well, we have to put no strong operator part, so we come in the usual norm theory. And let's say you want to put the normal relations, we want an element to be normal. So this is not enough to give you admissibility, because we can find the representation of normal elements unbounded norms, but we can then ask that the norm be less or equal to 1. So in other words, what this relation describing is a normal element in this orderly relation, just saying that the normal is less or equal to 1. And then the sister algebra yeah, so I can put just normal relations. Yes, so then set here. This continuous function. And close the disk.
Yeah, but is it unital? Maybe you should do also the unit.
Yes. It's true.
If you don't do this, what did you get? Zero.
Why do you need?
On the open.
No. Why do you need 1?
Because it's a compact. I think if you don't add the unit, you get the punctured disk, the disk without a point.
So this.
You have all x is less than 1, so you get all elements in the spectrum of x. It's automatically unitary.
But what's the unit of the algebra?
Well, you take the representation. So
No, you need the unit.
yeah, but
Oh, I think that if you perform this universal construction and do not include relations corresponding to something being a unit, you also always get something non-unital since it is universal. So there is no way that somehow unit magically appears. Yes.
If I recall correctly, if you just
we get C0 taking out 0.
yes, yeah. I think this example there, it's in Blackaddar's paper, that if you just take the sister algebra, you need to just let's put in.
Because this with the tender taken out.
Sorry?
This is different with the tender taken out.
Yes. Yeah, so it's another example. So X, X, these two relations. Just have to check with the recall correctly. This is gonna just give us.
Yeah. What will move me to 0?
Yes.
Instead of.
Another example is that one that let's talk about, so if I have this G, sorry,
It should be zero.
Zero. What kind of relation you
It's an ideal.
to impose in order to get C0 on an open disk?
for the open disk.
I thought that this example would lead to open disk.
So you have to kill the ideal of function vanishing on the boundary. Not at 0.
This. Yeah, I can check this for next. I did it.
It's open disk, then 1 minor. That's probably you have to the form operator relation. Something should converge to 0.
It should be the ideal. So this is the ideal of function vanishing at something described by the quality x equal to 0. Because everything is divisible by x.
Yeah.
So this should be the ideal
Yeah.
of
Sure.
say elements whose symbol map is 0. So these are compact.
Probably, but I imagine that you introduce this relation with this form operator topology relations. Something converges.
But the RS is 0 still. This example.
Yeah. No, right. Yes. You have to introduce some relation. It's yes, it's all these points. You
So now we have this infinite sum, and in this case. It's going to give us a quick. So I guess for Friday, I want to not give this example, only this one, but I want to work for a general graph system algebra that we could, if you wanted, define the system algebra of a graph, allowing the infinite sums for
RS.
So if you want to allow infinite sums.
And this is RS. The last relation is RS.
Yes. It's just because when we describe the relations, don't separate these two things. So, because when I appear in infinite sum, we just need to interpret this as being the strong operator. So next time I'm going to present the inverse property of these algebras, and then give an idea on how you build a homomorphism from this system algebra. That's the inverse property, and how you build a homomorphism to the system algebra. Then we use a certain paper representation. Then in the paper representation, the relation are satisfied. Then it's going to give us a map for this system algebra. And I'm going to do this next time because you have 1 minute, but it's John has to leave. I guess so I'll go stop here.
Okay. Okay. Can you? I just missed it. Can you tell me? There was a very interesting question. What is? What are the relations that give you functions on the open disk? You know, vanishing at the boundary.
I was just gonna check this. I want to check this example because I think this is done in Blackadder's paper. He gives a lot of examples. I remember gives this puncture disk, but I'm not sure if it's with the open disk or not. I have to check this.
If you took the norm of x is less than equal to
Yeah.
1 minus 1 over n for every n, so
Smaller than one.
what is this? Just
Yeah.
after the full.
No, that wasn't good.
Yeah.
Or more generators, yeah. Infinite generators.
Yeah, maybe.
Infinite generators with 1 minus n.
Yeah, I don't know. I
Then the same
Zero up.
x by n.
Okay.
Yeah.
Yes, right.
I'm gonna see if I can find this, but I don't know. Yes, now.
Well, maybe it's completely stupid, but how about this norm equality inequality being sharp inequality? Wouldn't it work?
Allowed.
Here for the theory that you gave.
Yes, but you can always replace one condition with big inequality by countable many with
The puncture something like this.
Yeah.
Well, can you give us generators for C0 of open disk?
That's the question.
Good question.
Because it's not it, right?
Yeah.
It's hope it's not that simple, right?
I mean, there's always
It's more complicated.
there is always the trivial answer that every sister algebra is generated by all the relations in the sister algebra. And so all the algebra is generators and
We're looking for the unqualified notion of elegance.
so yeah, so for the open disk I have to check.
Okay, but we leave it till Friday. So thank you very much. I'll stop recording now.